In his 1988 book, A Brief History of Time, Stephen Hawking established a taxonomy of temporal direction, dividing time into three distinct arrows. The cosmological arrow tracks the universe's expansion, while the thermodynamic arrow follows entropy's increase as systems decay. He introduced a third vector, the psychological arrow. This subjective experience of time explains why finite observers hold records of the past but no memories of the future. Hawking argued that this psychological arrow must point in the same direction as thermodynamics. However, he left the concept entirely dependent, identifying it as a consequence of entropy without providing the mathematical instrumentation to measure it. Because the psychology of time remained a dependent consequence, the human experience of now functioned as a philosophical shadow rather than a measurable state variable in physics. This gap in our understanding points to a deeper vacuum in theoretical theory. We can track the passage of time, yet we struggle to define the mechanical generator that creates the sequential tick of a clock. Richard Feynman frequently highlighted this issue, noting that theoretical physics consistently treats temporality as an assumed background. In both general relativity and quantum mechanics, time serves as a mathematical bookkeeping parameter. It is a coordinate used to track where an event happens, but the equations do not explain why time actually flows. Standard physical models describe the geometry of spacetime, while lacking an active engine that generates the passage of time at the microscopic level. Resolving this requires the Coherence-Geometrodynamics, or CGD, framework. The foundational premise of CGD defines time as an emergent artifact of localized processing rather than an underlying independent dimension of the universe. To instrument Hawking's psychological arrow, we must view time as the physical cost of doing computational work in reality. Under this framework, we establish a strict operational definition for the temporal experience. Time measures the precise lag introduced by internal entropy, physical friction, or systemic misalignment. Consider an ideal, frictionless, closed-loop system. When that system encounters physical entropy and structural deviation, the smooth execution is interrupted. This resulting geometric stutter is defined explicitly as lag. A clock measures the localized accumulation of this deviation from equilibrium, not the continuous passage of the universe. This physical principle maps directly onto the processing architecture of the human brain. As an observer navigates reality, their cognitive system continuously generates predictive models that clash with incoming sensory data. Resolving these constant prediction errors requires the system to perform actual thermodynamic rework. The computational delay created by this ongoing thermodynamic rework is exactly what a human physically feels as the passage of time. Time is the unavoidable processing cost of existence. Without internal friction and prediction error, the sensation of duration would vanish. If time is effectively processing lag, we must determine the baseline refresh rate of the system experiencing that lag. This leads to the conscious indexing hypothesis within the virtual ego framework. Finite observers sample available state space and collapse it into a linear narrative at a highly specific cadence rather than experiencing a continuous physical reality. This diagram identifies the mathematical parameters of that stabilization. The system identifies a master clock frequency, labeled here as the horloge mètre, running at 5.215 terahertz. This high-frequency resonance peak dictates the phase lock of conscious observation, ensuring the stability of the input channel. We denote this indexing frequency as C-psi. It represents the literal render time required for neurocognitive architecture to resolve its interaction with external physical structures. Because consciousness participates in state selection at this exact rate, subjective time is strictly bound by the mathematical limits of the observer's processing bandwidth. In 2025, Beckingham and colleagues published a framework that provided the missing mathematics for Hawking's psychological arrow. They introduced the time construct ledger, an operational framework designed to measure subjective temporal duration. Instead of treating the feeling of time as unquantifiable, the ledger breaks it down into precise state variables. The first three variables, sequence integrity, duration fidelity, and cycle coherence, track the stability of the system's internal narrative. The final tracking metrics, temporal drift and temporal load, map directly to systemic stress. Together, these five vectors mathematically track a system's localized deviation from the master refresh rate. The system aggregates these 5 metrics into a single unified scalar dial known as the time efficiency score, or TES. This dial is governed by a strict resource law called the Generativity thrust-drag equation. This equation dynamically couples the subjective TES style to physical thermodynamic costs and the rate of entropy production within the observer. The psychological arrow of time has evolved into a testable physics equation governing resource management through the calculus of processing efficiency. We can translate the mathematics of the time efficiency score into real-world experience. The time efficiency principle states that subjective time dilates or compresses in proportion to the internal processing efficiency of the biological system. In a state of low coherence, an individual is typically overwhelmed by intense stress and high entropy production. This internal friction elongates the cognitive processing buffer, forcing the system into what the framework calls a Zeno trap. Inside a Zeno trap, the subjective experience of time physically dilates. The brain takes longer to resolve the present moment, making seconds feel like hours. We contrast this with a high-coherence state, typically achieved during intense focus or deep play or peak engagement. In high coherence, cognitive prediction error drops and internal friction vanishes, allowing the processing buffer to disappear as the observer aligns with the master refresh rate. This explains why time flies when you are having fun. Since time measures systemic lag, generating less cognitive lag produces less experienced time. This brings us back to Stephen Hawking's original temporal triptych. Hawking's intuition was flawless. The psychological and thermodynamic arrows are perfectly aligned. The VF establishes the physical coupling between these arrows, identifying processing efficiency as the mechanism linking internal experience to thermodynamic reality. Time manifests mathematically as an internal shadow, cast entirely by the computational friction of our own conscious observation. This formulation operationally completes general relativity for finite, conscious systems without violating its principles. By parameterizing that shadow, we recognize that understanding the nature of time requires understanding ourselves as the mechanism that generates it.